Volumes of revolution. In this course, we're going to talk about two ways we can find the volume of revolution. In this section, we're going to talk about a method called the disk or washer method, and in another section, we'll talk about what's called the cylindrical shells method. Alright, so for our first example, let's find the volume of the solid created by rotating the region between y equals 4 minus 1/2 x and the x-axis over 0, 8 about the x-axis. First thing I'm going to do is draw it. What are we talking about here? Alright, well, the region y equals 4 minus 1/2 x. Hey, that's a line. Alright, so let me draw a line. 4 minus 1/2 x. Okay, so it has a y-intercept of 4, and the slope is negative 1/2. We can figure out that the x-intercept is 8, actually. And so we have this line, y equals 4 minus 1/2 x. So let me draw this line. There's a line rotating the region between that line and the x-axis over 0 to 8. So what I'm talking about is this region right here. And I'm rotating that about the x-axis. Alright, so let me sort of flip that picture over. And I'm going to sort of draw this dotted line here. And so what's happening is I'm taking that region and I'm rotating it about the axis. And so if you can sort of imagine what's happening here is I'm creating a three-dimensional object via this rotation. And our goal is to find the volume of that solid. Alright, now, if you haven't seen this idea before, that's okay, because, well, it's a brand new idea. And so what we're going to do is we're going to try and figure out how can I come up with this volume. And when we learned how to find area under a curve, what we did is we took a bunch of little rectangles and we added them up. Well, we don't really have rectangles here. Instead, what we have, in a sense, is I have this disk. Think of this as a disk, a circle. Alright, so I've got this circle, this disk. Well, for it to be a disk, it has to have some thickness. So what I'm going to do is I'm going to say that this disk has a thickness. I'm going to call that thickness delta x. Alright, now we have this disk. And I know I'm going to think of the disk as a very thin cylinder. Now that cylinder, I know that the volume of a cylinder can be defined as pi times radius squared times height. And what I want to do is I want to add up a bunch of very thin cylinders. Well, now if I think of this delta x as being the thickness, so now what I'm going to do is, well, if I think of that disk as being a cylinder, here's that same cylinder. Here's that same cylinder. It's very thin. It is delta x height, right? The height of it is delta x. And if I could figure out the radius of that, well, the radius is just this piece right here. That's the radius. And so if I'm talking about if this is some x value right here, then the radius, r, would be the function's value at that x, which in this case is 4 minus 1/2 x. And that's the function that we use to graph it. And so what I'm going to do now is I'm going to add up a bunch of these really thin cylinders. And remember, if we add up a bunch of really small things, we get an integral. And instead of a delta x, we think dx when we get to the integral. All right, so what am I doing? I'm integrating from 0, x equals 0, to x equals 8. Let's integrate from 0 to 8. All of these little cylinders. So I'd have pi. The radius is 4 minus 1/2 x, and I've got to square that. And then the height is dx. And now I've just got to carry out this integral. I can bring the pi outside. Integral 0 to 8. 4 minus 1/2 x, square that's 16. 4 times 1/2 is 2, double it. So minus 4x plus 1/4 x squared. I've got to integrate this. And so let's see, that's pi times the integral from 0 to 8. Let's see, that would be what? Oh, I don't need an integral anymore. Let me calculate the antiderivative. So let's see, that would be 16x minus 2x squared plus 1/12 x cubed, and over 0 to 8. And so now we go through the arithmetic here. 16 times 8, 2 times 8 squared. Let's see, I'd have pi. Let's see, I'd have 16 times 8, that's 128. 2 times 8 squared, 2 times 64 is also 128, so minus 128. Well, that's nice. Plus 1/12 of 8 cubed. 8 cubed, that's 512. Okay, so I'd have all of that, and then substituting the zeros, that's all minus a bunch of zeros. So 1/12 of 512, if we do some reducing here, we get 128 pi over 3. So that's the volume created by that rotation. That's the volume of the solid created by that rotation. And all I did again is I added up a bunch of little disks. Now, if you don't believe me, which is okay, I can handle that. Let's think about this for a moment. What shape did I create through this rotation? Let's look at this shape. Through this rotation, I created a cone. It's just tilted on its side. And I know from geometry that the volume of a cone is 1/3 pi r square h. 1/3 pi. The radius, the main radius here would be 4 units, and the height is 8 units. And if you go through the arithmetic here, 4 squared is 16. 16 times 8 is 128. That's 128 pi over 3. So what I've done in creating a bunch of really thin cylinders and adding them up, it works. It meshes, it works well with what we learned in geometry. So there's our introductory example, and there's the idea behind what's commonly called the disk method for a volume of revolution. So now in general, if we have a function, if we have a positive function over an interval a to b, then the volume of the solid generated by rotating that function about the x-axis is given by this formula, the integral from a to b of pi times f of x squared dx. What we can do is we can think of that as being the integral from left to right of pi times the radius squared dx. And again, the idea behind this is we are adding up a bunch of really thin disks. Alright, so here's another example. Find the volume of the solid created by rotating the function square root of 16 minus x squared about the x-axis. Again, I want to draw this. The square root of 16 minus x squared, hopefully you've seen something like this. This is the upper semicircle with radius 4. Right, so notice if x equals 4, the output is 0. If x equals negative 4, the output is 0. If x equals 0, the output is 4. And so what we get here is this shape. Right, this upper semicircle. And now what we're doing is we're rotating that function about the x-axis. So if I rotate it, I'll just do some sort of dotted here. I'm not a very good artist, so I hope you'll bear in mind that this isn't a perfect shape. But I'm rotating about the x-axis, so what's happening is I can think of there being these really thin disks. And so here's a really thin disk. And if I draw that disk, the thickness, I'm going to think of the thickness as being the dx. And then the radius of this disk, that r value, the radius is now not 4. The radius is the square root of 16 minus x squared. The radius changes depending on what x value I'm looking at. The radius is equal to root 16 minus x squared. And so again, I'm talking about the radius of that disk, not the radius of the semicircle that I've drawn. Alright, so I can now write an integral. The volume would be equal to the integral from negative 4 to 4 of pi times the radius, which is square root of 16 minus x squared, square times the thickness, dx. Now, I can use symmetry here. If we just sort of think about the shape, we can see it's symmetric about the y-axis. And so if we remember some of our rules for integrals, I can rewrite this as twice the integral from 0 to 4 of pi times, and I can simplify this. The square root of 16 minus x squared, that would just be 16 minus x squared dx. I can bring the pi outside the radical. So now I have 2 pi integral 0 to 4 of 16 minus x squared dx. 2 pi, let's find the antiderivative. That's 16x minus 1/3 x cubed. And evaluating at 0 from 0 to 4. So then that would be 2 pi. Substituting 4, that would be, what, 64 minus 1/3 of 64. Substituting zeros would give me 0. And so then 64 minus 1/3 of 64, we can do that arithmetic. And so that's 2 pi times 128 over 3. And so then that's 256 pi over 3 is the volume of that solid created by the rotation. Now again, if you remember some geometry, you might say, hey, wait a second, Joel. That's just a sphere. I know how to calculate the volume of a sphere. I had to memorize that formula back in geometry, and I know the volume is 4/3 pi r cubed. And my r would equal 4 here, and you get 4/3 pi times 64, and amazingly enough, 4 times 64 is 256, and so we get 256 pi over 3. Again, I'm just showing you, hey, this method works, right? This idea of creating disks and adding them up, it does work. Now, of course, most of the examples that we'll see will be examples that we cannot use a simple geometry formula for. So you're going to need to know this idea. All right, find the volume of the solid created by rotating the region between y equals x and y equals x squared about the x-axis. All right, again, let's draw it. What are we talking about here? All right, so let's see, y equals x. Well, that's just a line through the origin. Y equals x squared, that's our basic parabola. And so what we're doing is we're taking this region, all right, that's the region that's bounded, and we're rotating that region about the x-axis. And so then we'll get a shape that's sort of like this. Again, excuse my poor drawing, but through that rotation, now let's think about this for a moment. If I do that rotation, I'm going to get not a disk, because if I think about the disk, a disk is sort of solid. But wait a second, I got this hole in the middle. How do I account for that hole in the middle? All right, well, we'll figure that out in a moment. But how about what are my limits, right? Where am I integrating from and to? So if I solve the system of equations, where is y equal x and y equals x squared? Where are they equal? Well, that would be where x is equal to x squared. And so then 0 would equal x squared minus x. And so 0 would equal x by x minus 1. And so x would equal 0 and x would equal 1. All right, so they intersect at x equals 0 and x equals 1. All right, so now if I think about that washer, all right, it's not a disk anymore, it's a washer. If I can think of that as a very thin washer, again, I've got the dx as the thickness, but I can't just think of a radius, I have to think of an outer radius and an inner radius. And basically what I'm going to do is I'm going to find the area, the volume of the big disk and subtract the area of the inner disk. So then the volume of the washer would be pi times the radius of the outer radius square times the thickness, I'll just call it h for now, minus pi times the inner radius square, again times the thickness. And so with a little bit of factoring, we can see that this is pi times r outer square minus r inner square times the height. And so I can now set up an integral. I'll integrate, so then the volume would be the integral from 0 to 1, pi times the outer radius. Well, the outer radius would be the higher function, the upper function, which would be x. So I'd have x, and I have to square that, minus the radius, the inner function. The inner function in this case was the x squared. And I have to square that. And then the height of the individual disks is dx. I can again bring the pi outside. Integral from 0 to 1 of x squared minus x to the 4th dx. So I'd have pi, antiderivative is 1/3 x cubed minus 1/5 x to the 5th. And from 0 to 1. And so then this ends up being pi times, I'd have 1/3 minus 1/5, and then minus a bunch of zeros. And we go through the arithmetic here. 1/3 minus 1/5 is 2/15, and so then the volume is 2 pi over 15. Can't check this one with a formula from geometry. All right, so if we have a situation where we have not a disk but rather a washer, we can just adjust the formula a little bit, and we have to think of an outer radius and an inner radius. Alright, so here is that formula in general. If we have two positive functions where f of x is greater than or equal to g of x over some interval a to b, then the volume of the solid generated by rotating the region bounded by f and g about the x-axis is given by pi times the integral from a to b of f of x squared minus g of x squared dx. And we can think of that as pi times the integral from left to right of the outer radius square minus the inner radius square dx. And again, the big idea here is we're adding a bunch of very thin washers. Alright, so now we're going to just look at several examples and see how we can apply these concepts. Find the volume of the solid created by rotating the region between y equals 1/4 x squared and y equals 5 minus x squared about the x-axis. Alright, so here we have a couple of parabolas. One's opening up, the 1/4 x squared is opening up, the 5 minus x squared is opening down, shifted up 5 units. Let's draw it. Alright, so 1/4 x squared, that's going to be opening up, vertex at the origin, but sort of flatter than the standard parabola, so it might look something like that. 5 minus x squared has a vertex at 0, 5, and is opening down, so it might look something like this. And so we're talking about this region here. And we're rotating that about the x-axis. Alright, so if we draw our representative disk or washer, let me draw a disk here, we might have something that looks like this. But wait a second. Oh, there's a washer idea. Alright, so there's my washer. The outer radius is given by the 5 minus x squared, and the inner radius is given by the 1/4 x squared. Oh, but we got to figure out where they intersect. Alright, so let's calculate where they intersect. We will solve the system of equations. Where is 1/4 x squared equal to 5 minus x squared? I don't want to deal with fractions. Let me multiply by 4. X squared equals 20 minus 4x squared. I'll add the 4x squared over. 5x squared equals 20. Divide by 5, and x squared equals 4. And square root property, x is positive or negative 2. And notice that there's a symmetry about the shape. Alright, and I think we'll use that symmetry to our advantage. Alright, so then the volume would be equal to the integral from negative 2 to 2 pi times the outer radius. The outer radius was the 5 minus x squared minus the inner radius, which is the 1/4 x squared, and dx. Now again, I mentioned, hey, we can use some symmetry here. Again, notice that both of these are even functions, and so the region between them is also even. And so I can think of this as twice the integral from 0 to 2. I can bring the pi outside as well if I wanted to. And if I was going to do this by hand, I would start multiplying these out carefully. I would have 25 minus 10x squared plus x to the 4th minus 1/16 x to the 4th dx. And you know how to evaluate this integral. And so we would have 2 pi, and the integral ends up being 88 over 3. And so then I have 176 pi over 3 as the volume. Find the volume of the solid created by rotating the region between y equals x squared, x equals 0, x equals 2, and y equals 4 about the y-axis. Oh, we haven't done one like this before. We haven't seen one where we've rotated about the y-axis. All right, well, let's see what happens. I'm going to draw it first. All right, y equals x squared. That is our basic parabola. X equals 0. That is oops. Sorry about that. X equals 0 is the y-axis. X equals 2 and y equals 4. All right, so let's make that 4. So x equals 2, y equals 4, x equals 0. So we're talking about this region right here. And we're rotating that about the y-axis. So now if we rotate that about the y-axis, we get that three-dimensional figure. But now if I draw a representative disk, my disk would look like this instead. There's my disk. And now the thickness of the disk is not a dx, but a dy. And if I was thinking in terms of y, well, I don't want to think in terms of x's. If I've got a dy, I need to think in terms of y. So I'm thinking from y equals 0 to y equals 4. And now I would need my radius. If I think of my radius here, I have to have my radius in terms of y as well. And so if y equals x squared, then x would be the positive square root of y. And so what I'm going to do is I'm going to set up my integral, but instead of in terms of x's, I'm going to think of it in terms of y. And so then the volume would be the integral from y equals 0 to y equals 4 of pi times the radius. Now remember, if I'm thinking in terms of dy, I would have to use the square root of y as my radius, and that's being squared. And so then my volume would be pi times the integral from 0 to 4 of y dy. That's pi times 1/2 y squared from 0 to 4. And if you go through the arithmetic here, we end up with 8 pi. And so we can do this, right? All we have to do is change our way of thinking. If we draw the shape and after the rotation we see that our representative disk would have thickness dy, then we have to adjust our integral to be in terms of y rather than in terms of x. Find the volume of the solid created by rotating the region between y equals 3x, y equals 0, and x equals 4 about the y-axis. Now would be a great time to pause and try this one out on your own. Draw the region, draw the rotation, see what the shape would end up as, and then choose your approach. Alright, let me draw the region first. I've got the region between y equals 3x, so that's just a line with slope 3 passing through the origin. Y equals 0. Y equals 0, that's the horizontal axis, and x equals 4. Okay, that's a vertical line. We're rotating about the y-axis. Alright, y equals 3x. Alright, so y equals 3x. Looks like this. There's y equals 3x. Here, let's say that this is x equals, there's 1, 2, 3, there's x equals 4. y equals 0, x equals 4. All right, so this is my region. And I'm rotating that about the y-axis. All right, so I would have, this is the counterpart on the other side. All right, so what I'm going to do is I'm going to draw it like this. There's my representative disk. And again, now, the disk has thickness dy. I say disk washer. My lower boundary is at y equals 0. My upper boundary, the upper boundary, if x is equal to 4, then y would equal 12. My outer radius, well, if I look at this shape, the outer radius is always 4. The inner radius is this distance right here. That distance, remember, we have to think in terms of y. So if y equals 3x, I have to invert that function. If y equals 3x, then x is equal to 1/3 y. And then my integral for the volume would be the integral from 0 to 12 of pi times the outer radius square minus the inner radius square dy. I can bring the pi outside. And simplifying, I'd have 16 minus 1/9 y squared dy. And we can go through the calculations. We know how to find this antiderivative and to substitute. That's not the difficult part here. We end up with 128 pi as the volume. So the difficulty is in setting up the appropriate integral. And then we know how to find the antiderivative and substitute using the fundamental theorem of calculus. All right, in all of the previous examples, we've been rotating about either the x-axis or the y-axis. In this last example, we're going to rotate about the line y equals 20 and see what happens. Find the volume of the solid created by rotating the region between y equals x squared plus 6, y equals 4, x equals 0, and x equals 3, about y equals 20. All right, as before, let me draw it. All right, y equals x squared plus 6. Well, let's think ahead a moment. Let's make this 20. There's y equals 20 right there. I've got to rotate about that line. So let's just sort of think ahead. Here's my x-axis. Y equals x squared plus 6. Well, that's a parabola opening up with a y-intercept of 6. So it looks like this. All right, now y equals 4. Well, y equals 4 is here. There's y equals 4. X equals 0, so that's the vertical axis, and x equals 3. So let's say here's x equals 3. Right, so there's the line x equals 3. And so what I'm talking about is this region right here. This is the region, and I'm rotating that about y equals 20. And so I'm going to end up with a shape that looks like this roughly on the other side. And now let me draw my representative disk. This is going to be a very, oh, that was bad. So let's draw this disk. And now let's think about, well, wait a second, it's not a disk, it would be a washer. And we've got to figure out what's the outer radius and what's the inner radius. Okay, and first, its thickness is dx. What's the outer radius? Well, the outer radius is constant, right? It's always, let's see, it's the distance between 20 and 4. The outer radius is always 16 units. The inner radius, though, the inner radius changes. The inner radius, right here, this distance right here, let me draw that and distinguish it. This distance right here would be 20 minus x squared plus 6. And so then that would be what? 14 minus x squared. And so now once we've got that, once we figured out those pieces, the volume is easy. The volume would be the integral from 0 to 3 pi times the outer radius, 16, we got to square that, minus the inner radius, 14 minus x squared, and that whole thing has to be squared, dx. And we can go through all the arithmetic. That's pi times 1917 over 5. Just trust me on that one. Or use your calculator. And 1917 over 5 times pi. Alright, so that was how we can approach volumes of rotating a region, volume of solid by rotation, using disks, washers. We have another approach that's called cylindrical shells, and that's in another video.